ended up with the training of CNN, right? And then at the very end, I mentioned that we have this problem with the vanishing or exploding gradient, right? What we want to do today, we want to just discuss this idea of skip connection or residual learning. And this idea is eventually developed to address this issue of vanishing or exploding gradient. So let's just have first a bit of history about CNNs, because CNNs are the one which made deep learning quite serious. So the initial version is LeNet, or as I mentioned before. So it was developed by Jan LeCun. It was, I guess, 1998 or something, the original paper. So at that point, they developed this idea that, well, Fukushima had done it before, but it was the first time that they really computationally discussed it, and then they developed the backpropagation algorithm for vision training. So this guy is the LeNet, the original, the very first one, which has, as you can see, is basically 2 layers of convolution. So one convolution, one pulling, the other convolution pulling, and then one MLP at the very end, and it was working fine in recognizing the letters. If you check the original paper, I put it on the web course, on the web page of the course. So they did implement this. They say, oh, it shows lots of potential, but at that point of time, people were not very happy because they did not believe that there is too much, say, capacity in going this direction. And then the story was somehow left as a kind of, interesting idea, but inside the literature for quite some time. And then in 2010, it was the ImageNet challenge. I don't know if you know about ImageNet. I think I mentioned it before. So when we talked about VGG, I told you that it was originally, the samples that we had was coming from ImageNet. So ImageNet challenge competition started in 2010, and what was the idea? So 1.2 million images collected, all of them 250, I think 240 or 250 by 250, I think, resolution. So high resolution, 3-channel RGB images. And there was 1.2 million images. They later just added to those images, and then they had 1,000 different labels. So it could be cat, dog, bird, car, plane, lots of other things. And what they wanted to do, they wanted to have one algorithm which looks at the image and says what is the class. And then afterwards, gradually they started to increase the tasks. Like, for example, they wanted segmentation. Like, you look at the image and you identify where are the different objects inside the image, right? So they did this challenge. They introduced this challenge. And every year, people just propose their own solution, and they give the solution. They test the solution on a specific test set, and the highest accuracy or the lowest error would get the prize. So the winner in the first 2 rounds, they were basically no neural networks. They were shallow, rule-based, basically, algorithms. So they look at the image, they just compute a bunch of, functions out of the pixels, and then they tell you what is inside the image. So these 2 guys, 2010 and 2011, they were not neural network at that point of time. Deep learning was not still a thing. And it was actually 2012 when the supervision team from UofT just won first time with a deep neural network, the ImageNet challenge. So this is the AlexNet, the one who won 2012 challenge. And as you can see, you have here one convolution layer, then you have max pooling, and then again another convolution layer, max pooling, and so on. So it was basically a kind of extension to LeNet. They tried a lot of hyperparameter tuning to make it work. It took them a long time to just make it train, because at that point of time there was no PyTorch, right? No TensorFlow, nothing like that. So everything was implemented from scratch. And people, it was basically a massive thesis. And then people could just train this one. It was performing much better than the other benchmarks that were developed in the last 2 years. So they won this challenge. So the proposal had 8 different layers, so 5 convolutional layers and 3 fully connected layers at the output. And it could just reduce the classification error significantly, which was the point when people started to have some, some feeling that deep learning is really working. So it's not just a story. So people from then on started to work a lot on deep learning, just for computer vision. And after that, any winner of this competition was a deep neural network. So no rule-based anymore could win this competition. You can guess nowadays, this is quite obvious to you because that neural network is significantly more capable of any other rule-based approach. But at that point of time, people were not still really believing that because they were actually not believing that all of this backpropagation and stochastic gradient descent is going to eventually work. So 2013 was not a very big jump. So it was basically AlexNet again. They just tried to do hyperparameter tuning. As I said, nowadays this is quite simple thing for you. But at that point of time, it was a hard thing because people had to do all the implementation by themselves. And we were not as good in computation as we are today, right? So 2013 was the same thing. So, people started to work on that one again. So they added some layers, dropped some layers, tried to play with the sizes of the layers and other hyperparameters. One thing that people concluded at this point of time was that, well, since backpropagation is working, since stochastic gradient descent is really working, so the key is depth, right? The deeper you make your neural network, the more capable your neural network would be. Well, people theoretically knew that based on the old, universal approximation theorem developed in the 80s. But the point was that they did not think that it's applied thing, like they can implement it. But now that they see that it can be implemented, so their conclusion was that, well, we can go deeper and deeper, and the deeper we go, the better we're going to get the result, right? So people started to just go deeper. And VGG, the one which we discussed in chapter 4, was the one which won 2014 challenge. And they proposed 4 different variants of VGG, so 11 layers, which was still deeper than AlexNet with 8 layers, and then 13 layers, 16 layers, and 19 layers. And they just tested all of them, reported all the results, like showing the deeper you are going, the better you are getting. Okay? So this was the VGG group in Oxford University, just coming with that idea. But there was some observation that they had in their paper. They just reported it, but at that point of time, well, they were not still clear whether this is really an issue or not. So what was the issue there? The issue was that when they started to working with 11, 13, 16, 19, the deeper they go, the accuracy is getting better. The error is dropping. But from 11 to 13 is dropping significantly. From 13 to 16 is again dropping considerably. But from 16 to 19 is very minor, very marginal. So they did not know whether it's simply because, the problem, this is the capacity we could reach, or maybe there is some issue like overfitting or something happening. But they reported this, that the improvement as we go deeper is getting more and more marginal. So that was the result they showed. So the top one is VGG 11, so 11 layers. This is 13 layers, 16 layers, 19 layers. And as you can see, error is dropping more and more. So here, for example, it drops 0.5%. Here it drops significantly more from 13 to 16. But from 16 to 19, it's just dropping with 0.1%. As I said, they just reported it. They did not flag any specific issue. But this was somehow interesting for people to look into it to see, okay, say now instead of 19, we go for much higher number of layers. Would we get like from 8 to somewhere close to 4 or no? We are going to, for example, saturate at 8. So just as a kind of note, maybe you hear this when you read something. So there is also some other kind of architecture proposed in 2014. So it was also among the winners of the ImageNet Challenge. This was the Google Perceptron, I guess. Yes, Perceptron. Sorry, Inception, not Perceptron. Inception module. So the Inception module proposed by Google was basically, again, a CNN, but the CNN was, like the whole network was built by convolutional layers. There was no fully connected layer involved. And the key point was that they could just reduce the number of parameters, because you know that convolutional layers work with filters, and filters have less parameters as compared to a fully connected layer. So this was their trick. They could, I guess they won the segmentation task in the challenge. I do not remember exactly, but I know that they were among the winners. And yeah, nowadays still you hear Inception module. Sometimes you read some paper and they say, like, for this task we just used an architecture purely based on Inception, and that simply means that they just collected a bunch of convolutional layers and tried to configure an architecture which solely works with convolution. It doesn't work with fully connected line. Okay, but back to our main story. Oh, it was the classification test. Sorry, so the other one was segmentation test. The VGG was segmentation test. Okay, now back to our story. So the key point that people started to see was that now, okay, if we go deeper than VGG 19, what's going to happen? They started to see that, well, they are not getting really improved. And eventually, they did not need to go very deep to start to see that the deeper they go, actually the performance is getting worse. So that was something they started to see. So the performance started to get saturated. Then when they go deeper, so they just increased up to 22 layers, and it was somehow not changing anymore from 8. And then going after 22 layers, the higher they go, they start to see worse performance. Like the accuracy is dropping, the error is just increasing. So what is your explanation for that? What do you think is the reason? Yeah, overfitting is the first explanation everybody gonna say, right? So everybody thought at that point of time, well, this is overfitting. But Microsoft people did some experiment to prove that this is actually not overfitting. So this is the result that they showed in their paper. And what they are doing here, so this is the number of iterations you are doing your gradient descent, okay? And this curve that you see is the loss, or the error you get when you are doing training. So this is not test, this is not generalization, this is exactly your training loss, like the training loss you get after every iteration. And this is your test loss, test error, okay? And as you can see, your training error is dropping. This yellow curve is for 20 layers. The red one is for 56 layers. Same thing is happening here. Can you tell me why this curve is explaining no overfitting inside the network? Now, go ahead. Yeah, yes. You just go ahead. Yeah. Right. Right. So if it is overfitting, what you need to see is that this red curve, 56 layers, this guy should be better than the yellow curve when you are training, right? Because your model is getting trained, it's just simply overfitting, right? When it overfits, it's going to perfectly match the training data, right? And it's going to work perfectly there, right? So red curve should be below the yellow curve, right? In training. And then when you do test, then it's going to just go up, right? Because it's just not generalizing, right? So if the red curve was below this yellow curve and we had this test behavior, then it was overfitting, right? But this is not the case here, right? When we are training and we are testing, in both cases, the model with 56 layers is just performing worse, right? So it simply says that this is not overfitting, right? So this was the conclusion they got out of this study. So what they concluded was that, okay, if it was overfitting, we had this red curve below when it was about training, but this is not the case. So since both training and testing are performing worse with 56 layers, it simply means that our model is not getting trained, right? So you are increasing the depth, but your model is getting worse in terms of learning, right? So what is the reason then? So the main reason that, at that point of time, to be honest, many people started again to blame backpropagation, right? Backpropagation is not working. We told you it's the time, finally, right? It's not like since 80s when people started to write the paper in Nature about backpropagation. Everybody's saying, no, it's not working. It's all about backpropagation. But people at that point had a good understanding of what we call it vanishing gradient, because they used to work with sequence data, and with sequence data and recurrent networks, you see it immediately because you backpropagate through time. And people started to just blame vanishing gradient, which was actually the point. Like the vanishing gradient was the main issue. So this is just a summary of what happened up to that point. So here, this is 2014. And what you can see here is that you initially had your shallow or basically rule-based approaches, which were very high in error. And then gradually we started to decrease the error by increasing the depth. So we just go for deep approaches. And the error, the classification error, is just dropping. And the number of layers is going up, okay, through time. But at this point, somehow people got stuck. So people said, like, if we go deeper, we don't get anything. And then the issue was basically the vanishing gradient. So what is the idea of vanishing gradient? In simple words, if you have a very deep neural network, how do you compute the gradient of every single weight inside this network? We just put your data. We send it over the network. You're going to get to the output. Now that we are at the output, we just compute the output gradient, right? And we backpropagate all over the network, right? The deeper network gets, the more this gradient needs to propagate, right? It means that every time it needs to get multiplied with a bunch of other gradients, right? And if all of these gradients are small numbers, this gradient started to get smaller and smaller and smaller, right? And once you are at the early layers and you want to update your weights, then your gradient at that point is quite small, right? And your weights do not get updated properly, right? And because of that issue, your model stops to learn, right? Because it's so deep that the weights at the very beginning are not getting enough gradient to get right, to know what is the right direction to improve, right? So that is the main idea of vanishing gradient. You can have the same behavior, which we call it exploding gradient. It means that the gradient is every time, after every multiplication, is just getting larger and larger. And then gradually, at some point close to the beginning of the network, it's going to be extremely large so that it's actually clipping all the weights, right? So the weights just get out of the precision they have on the computer, right? So this is the issue, but you might just find my explanation totally intuitive, right? And how we can understand it concretely if we want to really practice it a bit more. So, well, the best idea is to just do what my friend says, right? My very close friend. So this is very well-known saying by Einstein that he says everything should be made simple as possible, but not simpler. And of course, we want to do the same thing. We want to just understand this vanishing gradient for the simplest kind of neural network we can think of, basically a scalar neural network. It just takes any scalar input. It just goes deep to compute the output. And we see how does this vanishing gradient look like, why it shows up, what are the components that are making this vanishing gradient, and how we can get rid of it. Everybody's cool? Questions? No question? OK, so OK, let's just consider this dummy neural network. So we have this scalar neural network. It has L different hidden layers. And it's simplest neural network you can think of. So it's going to take single scalar input. It's going to give you a single scalar output. And I consider activation in all layers to be the same. So this is basically your neural network. X is a scalar, just one number, gets multiplied with one weight, then gets activated by F. Again, the output is multiplied with W2, activated, and so on till the last layer. This is that last hidden layer. When you get the output, then you activate the output. So WL plus 1 times the last output, and then you're going to get your last hidden output, hidden feature, and then finally you're going to get your output theta, OK? So this is still a neural network, right? It's not very wide. I mean, the width is 1, but the depth is quite, it could be very deep, right? L if L is very large. So Y1, the first feature that we compute is activated version of W1 plus X, times X. Y2, computed from Y1, and so on. You go to YL, and finally you compute your output theta to be the activated version of the last feature, right? Everybody's cool, yes? So this is a neural network, and we can, I mean, even though it's quite dummy, we can still write down the backpropagation algorithm for this one, right? So let's say that we want to just, for example, compute the gradient with respect to all the weights, right? So it means that I put one x here. The x goes and compute every single feature in between. I'm going to get the output. Now I am at the output. I want to know what is the gradient of the loss, or the derivative of the loss, with respect to every single weight w that I have inside this neural network, right? Once I have those derivatives, I can update, correct? So what should I do? I'm going to start with the output, correct? The first thing I do, I'm going to take the derivative of my loss, r hat, with respect to the very output theta, right? Can I compute that? Yes, I can do, because I get my theta, I have my true label. I compute the loss between them, for example, MSE, or cross entropy, or whatever, and then I take the derivative of that function. So that is not a big deal, right? Now, what should I do next? I should go one step backward, right? So I have the derivative with respect to theta. I need to take the derivative with respect to the last feature, right? So I would say the derivative with respect to theta is given. So now I do know that theta is f of this guy, right? And I want to just know what is the derivative of r, the loss, d of r hat, with respect to my last feature yl. How can I write it down? I can write it down by chain rule, right? So this is what we have done all the time. So we would write, OK, derivative with respect to theta, the last thing that I had, times derivative of theta with respect to yl, right? What is derivative of theta with respect to yl here? What is derivative of, let me just take this a bit up. What is derivative of theta with respect to yl? This is f prime, exactly, at the point WL. Is it WL plus 1, sorry. L plus 1 times YL, right? Times the derivative of the argument with respect to YL, right? Chain rule, correct? So this guy is actually your ZL, right? So this is derivative with respect to ZL times derivative of ZL with respect to YL, right? Which is WL plus 1. OK, you see it. So this is the guy, right? So I have my first derivative. So this is derivative with respect to theta. I'm going to keep it. This is what I got out of backpropagation. Then I have my last weight times the derivative of the activation function, right? OK. Now, I want to go for the next one. So I want to know what is the derivative with respect to yl minus 1. What should I do? again, I repeat the same thing, right? I do have the derivative with respect to YL. I computed it here, right? So I would say the derivative with respect to the previous feature is basically the derivative with respect to YL, my last feature, times derivative of YL with respect to, here is YL minus 1. It's a typo, sorry. So the denominator is YL minus 1. So what is derivative of YL with respect to YL minus 1? Look at this function. What is the derivative of my last feature YL with respect to Y? It's the same thing, right? It's again a weight times derivative of the activation function. So I can write it down again like this, right? But this YL, it was itself derivative with respect to theta times another weight and another derivative, right? So I can write it down in this form, correct? So derivative with respect to output times my last weight times my previous weight times derivative with respect to derivative of the activation function. What's going to happen if I just go all the way back to y1? I'm going to have all the weights getting multiplied, all the derivative of activations getting multiplied, correct? So if I keep going on up to y1, then for y1, again, I could say this is derivative with respect to y2 times derivative of y2 with respect to y1. y2 to y1, again, looks the same, right? It's going to be w2 times derivative of the activation, right? And then, again, derivative with respect to y2 was the same thing, and so on. So this is the whole recursive behavior that it has. So it's going to end up with such an expression, right? Everybody's cool? So derivative with respect to output times multiplication of all the weights that I had on the way times derivative of all the activations I had on the way, right? Everybody's cool, right? So that is the derivative with respect to y1, right? Now, what do I want at the end of the day? I want the derivative with respect to weights, right? Correct? Like, I want to know what is the derivative of my loss with respect to weight 1, weight 2, weight 3, so that I can update them, right? So if I want to compute the derivative with respect to weight 1, what should I do? I can simply say that derivative with respect to weight 1 is derivative with respect to y1 times derivative of y1 with respect to weight 1, right? Is there any other immediate function of weight 1 in this architecture? Is there anything but y1 which is directly computed by weight 1? No, right? So I do not really need to keep on going more, right? There is no other term here. Everybody's clear, right? Everybody's cool, right? So this guy is basically the only term that I have. And if I just write it down, it's going to be derivative with respect to y1 times derivative of y1 with respect to weight 1. That guy is, again, the same thing, right? X times derivative of activation, right? So I'm going to keep x times derivative of activation here. That's fine. And this guy is that term that we computed in the previous slide, right? That derivative with respect to y1 is actually all the weights multiplied, all the activations multiplied, right? So it's going to look like this guy, right? You see it? Everybody's cool? So this is our derivative with respect to weight 1, right? Our derivative with respect to weight 2, again, looks the same, but it's going to have one term less, right? Because you need to do this when you get at y2. You don't need to go back to y1, right? Your derivative with respect to w3 is going to be, again, the same term with 2 terms less, right? 2 multiplication terms less, right? So as you go deeper, these multiplications are increasing, right? So it means that the weight in the first layer is taking the most number of multiplications. The weight in the last layer is taking the least number of multiplications. It makes sense, right? Because when you are at the output, you can immediately know what is the derivative with respect to your last layer. But with respect to the previous layer, you still need to backpropagate, right? OK, cool. So this is the term that we have for our derivative with respect to weight 1. So this is derivative with respect to output times accumulated backpropagation, right? This term, this giant term, is the term which has been accumulated through backpropagation for us, right? Now, first of all, let's see how does this term behave if we have very deep neural network. L is very large. Let's look at this one. So I want to consider two different cases. The first case that I consider is the case where all my activations are simply sigmoid function, okay? Now, if I have a sigmoid function, what is the derivative of sigmoid function? I think you have done it in your assignments quite some time. If you have sigma, the derivative, what is the sigma, the sigmoid, what is the derivative of this guy? You can open it up. It's going to be sigma x times 1 minus sigma x, right? It's going to be, when you write it down, it's going to look like this, right? Now, looking at this term, derivative of the sigmoid, can it be more than 1? Sigmoid is not more than 1, right? It's between 0 and 1, right? So sigma is between 0 and 1. 1 minus sigma is between 0 and 1. This term is definitely between 0 and 1, right? Can it be 1 exactly? No, right? It cannot be 1 exactly, right? I mean, sigmoid itself is never 1 exactly, right? It starts close to 0, never 0, goes up, and it gets close to 1, never exactly 1, right? So this term, this derivative, is definitely something smaller than 1. If we play with it, we might be able to make it close to 1, but this is not exactly 1, right? Everybody's cool, right? So now, if I want to just replace sigmoid, where does it show up in that upper term? What guy is sigmoid now? F, right? OK, great. So now the point is that this derivative of f, when I assume that f is sigmoid, is simply smaller than 1, right? First thing. Now, the next thing, OK, I would say, let's say that this f prime is something, is smaller than some number a, right? And this number a is not 1, is smaller than 1, but as it can be close to 1 as much as I want, right? And this is correct, because I'm talking about sigmoid, right? The derivative of sigmoid is definitely smaller than 1. Then I choose a to be, like in this example, 1 minus 10 to the power minus 10, for example, right? You can always find one number which is smaller than 1, right? It's not exactly 1. And it's bounding all of these derivatives, right? So it doesn't matter what is the input of your sigmoid, the derivative is always smaller than a, right? So that could happen. So let's say that this number exists. It definitely exists, so say we call it a. And now what I want to do, I want to see how does that term look like. So the term that I have there at the top is this term, right? Correct? Now, one thing that I guess I am dropping here. Oh, OK, no. One thing that I am also considering is that you assume that all of your weights are also smaller than 1. It's not actually going to impact so much, but let's, for simplicity, we assume that they are all smaller than 1. And it could very well be. If you're updating by sigmoid, eventually at some point your weights are also getting updated by those gradients, which are very small numbers. And they're going to converge somehow close to 1, assuming that your other things are all normalized. Your input is normalized and other things. So if that is the case, then this term derivative is smaller than a, right? This weight is also smaller than a, right? And how many of these terms I have? I have here L of them, right? Here again L of them, and then I have one else here. So this whole term is going to be this derivative with respect to output times x. This is going to remain here. And all of this multiplication is going to be smaller than a to the power 2l plus 1. Everybody's cool? So you see that, right? Yes? The weight being smaller than 1 is an assumption, right? But if it is not, then it's still, I mean, you're going to see that this is not going to really impact too much. Everybody's cool? So now, what I do have, I have my derivative with respect to the first weight. It looks like this, right? It's smaller than some constant term, which is my derivative with respect to output times my input, times one term a to power 2l plus 1, right? Now, even if a is as close as possible to 1, if I just take it to power 2l plus 1 and I increase this value of l, what's going to happen? This is going to be 0, right? It gets very, very close to 0, right? You can try it on your computer. It doesn't matter how close you make it to 1. Eventually, when L is large enough, this is going to concentrate around 0, right? So this is, and actually in practice, you don't really need to increase L too much. Like if it is 100, then it's practically 0, right? So one thing that is going to happen here is that when you increase the depth of your neural network, your derivative with respect to the first weight is going to be eventually 0, right? And it doesn't matter how accurate you do your computation. At the end of the day, this value is very small, right? Now assume that your weight W1 started from some value, right? Now, every single time that you want to update with a very deep neural network, this is going to get a gradient which is very small. It's practically 0, right? And you get this gradient, you multiply it with a learning rate, I don't know, 10 to power minus 3. You even make it smaller, and then you just subtract your weight from that, right? Basically, your weight does not change, right? So the first layer is actually not getting trained at all, right? Now, you do not train your first layer. The feature that is extracting for you is a sort of random feature, right? And every learning happening after that is just based on that random feature, which is useless, right? So this is why your neural network is not really learning anything, right? So this behavior is what we call it vanishing gradient. And you see that if you want to have vanishing gradient, you need to have weights which are not necessarily as small, because here I just said a, right? But if I say my weights are bounded, this argument is still correct, right? If I say, for example, instead of a, my weights are smaller than something like 10, right? Well, it's going to be one big number, so the constant is going to be big. But that a value is appearing enough that it's going to just kill everything, right? So moral of the story, when you have a very deep neural network, and you have, for example, activation like sigmoid, then eventually, in a very deep architecture, in the very beginning layers, you're going to get gradients which are practically 0, right? This behavior is what we call it vanishing gradient. And theoretically, or if you want to be a bit more rigorous, you would say that your gradient is going to concentrate around 0, right? So it means that practically, in practice, whenever you sample one gradient, that is pretty much 0, right? It might be out of few samples. One of samples just give you a huge gradient, and that impacts the first layer a bit. But if you randomly choose one sample and you compute its sample gradient, it's going to be eventually very close to 0, right? So this backpropagation accumulation term is going to concentrate around 0, and this is why your first layer is practically not getting trained at all, right? Now, we can consider one other case as well. The other case is that we have ReLU function as our activation, okay? And again, just to keep things simple, assume that all the inputs going to the activation function right now are positive, okay? This means that your ReLU function derivative is simply 1, right? So ReLU is linear when your input is positive, correct? And its derivative is simply 1. So that derivative f dot is going to be 1. So this guy is going to be 1. Okay? And this is going to disappear from the accumulation term. The only terms remain are weights, right? Now, one thing else that, again, what you can say, let's say that those weights are tiny bit larger than 1, right? Maybe 10 to power minus 10 again, right? But they are slightly, all of them, just we started randomly, and they are slightly larger than 1. What's going to happen? Everything goes up, right? So again, you could say that if there is one a, which is slightly more than 1, then this multiplication is going to be bounded from below by that number to power L, right? And then as L increases, that a to power L is getting bigger and bigger and bigger, and eventually it's going to explode, right? So it's going to get you to values for gradient which are eventually impossible for your computer to present with finite precision, right? And your computer is going to just, float, just shoot the overfloat of the possible precision, right? So this is the other case. This is what we call it exploding gradient behavior. It means that the setting is in a way that your weights are all, or your gradient is just going to keep increasing as you go deeper inside your neural network. And your update is going to just explode, meaning that after the first update, your weights are getting to just hit the precision of your computer, and they never get updated anymore, right? Again, they do not get any learning, right? So if you want to be, again, a bit concrete, you would say that it's going to concentrate in infinity. So moral of the story, when you have a very deep neural network, your gradient, if you randomly just compute one gradient in a very first layer, is always concentrated around 0 or infinity, right? Yes?
So it appears that this problem is related to the activation function that we are using, right?
Right.
We cannot find one function that solves these two problems.
No, really. I mean, one of the reasons, so this is what I show in mention in the next slide. One of the reasons that we are happy with ReLU, one of the reasons, is basically this one. Because when it has gradient, it's 1, right? It's not showing. So you need, the only way that you do not see that behavior is when all of your weights and all of your activations are concentrated around 1, right? Because 1 multiplied so many times is going to remain 1, right? And this is one of the reasons that batch normalization and ReLU function are going to help the stability of your training, because both of them concentrate you somehow around 1. But again, if you go very deep, this is not that helpful. Just in moderate depth, it could be helpful, right? So, everybody's clear? Questions? So, moral of the story, if you go very deep with your neural network, the thing that is going to happen is that the deeper you think, like the very earlier layers, their gradient is going to go either exploding or vanishing, right? And one thing that is usually happening is that vanishing is more frequent as compared to exploding. You can guess because usually you have activations which give you derivative is smaller than 1, right? And your weights, you usually do normalization, so your weights could eventually be smaller than 1, right? Many things you might do in practice to just keep your values bounded, right? And this means that when it wants to just choose between these two behaviors, it's usually vanishing. So this is more evident behavior than exploding. But exploding, you can also see it, especially if you are, for example, training again. You can easily see the explosion because there, or RNN you can also see there because, it's deep enough that just a single tiny bunch of weights happening in between can just explode everything. So, now, the thing that we would like to have is that the derivatives that we want or we compute are mostly concentrated around 1, because if all of them are around 1, then multiplying them is going to just keep them around 1, and then it improves, it just reduces this behavior of vanishing or explosion. So this is one of the reasons, as I told you, that ReLU function, one of the reasons, not the only reason. I mean, ReLU is also very simple in terms of implementation. It's halfway linear, so these are the key points about ReLU. But one of the reasons that we are happy with ReLU is also that when it has gradient, the gradient is 1, right? Which means that it can slows down this behavior, right? This is one of the things. The other thing is that why we did normalization. I mean, at that point of time, I simply told you because you want to just concentrate your data around a specific center and you just make it uniform. Unit variance around it. But this is also another reason, right? Because you want your weights, when your data X is normalized, then your feature and your features are normalized, then all of those derivatives you compute are, again, within the range of 1, right? Concentrated more around 1 and makes this behavior slower, okay? Now, even though these two key observations are important, and at that point of time, people were just saying, okay, if you see vanishing gradient, just try to play with your activation, try to just do better normalization. Maybe you do linear normalization as well, and this is going to help you. But this is, again, going to help you up to some point, right? It's not going to help you forever. And when you go very deep, then just using ReLU and doing normalization alone is not going to help too much anymore. So these two solutions are like hands-on, old-fashioned solutions, but the more novel solution to this problem is what we call a skip connection. And skip connection was actually proposed in the same work that I showed you by Microsoft. So they actually first showed that behavior. They concluded this is coming out of vanishing gradient. And then they said that we do know that you have these two other solutions. You can play with your activation. You can do normalization. But what we can see here is that these solutions are no more helpful when you go very, very deep. And what is the remedy for that? We're going to propose what we call a skip connection. Okay? And now this is basically what we want to discuss next.